Okay. Hello everyone and welcome to this next lecture of Python Power Electronics, and in this lecture I'm going to talk about some of the normal or rather common bugs that you can find while running the circuit simulator. So now there are a lot of bugs and some of them may be a little deep, particularly when you get into the part of actually having your own control functions. But for now I'm going to talk about just the basic bugs which might usually happen when you start running a circuit simulator. So to begin with, I start again with my command prompt, and this is in my virtual environment directory. So first things first, I need to activate my virtual environment. So I am now within the virtual environment. So now the next part is I must go into my circuit simulator. This has already been set up, and if you have a doubt, this is part 2. So therefore, if you have a doubt as to what I'm doing here, please go and see part 1, and that is part 1, how to simulate a circuit. And this is the continuation of that one. So I'm going to continue the same simulation, that is simulating a diode rectifier fed by a single phase source with two resistive loads at the end. One is a constant load, one is a switch load. So to get started with this, I already have everything set up. So all I need to do is launch the server. So the server is running. I shall copy this address and paste it. So I'm going to paste this in my Google Chrome, and I get my circuit simulation welcome page. Now in the previous case, when I click circuit simulation library, there was nothing because I had just installed the circuit simulator in my virtual environment. Now I'm going to click it again, and now you see it has saved the simulation which I created last time. The last simulation which I created was the diode rectifier with switch load. So you can now reload the simulation. I don't have to do it again. So I'm going to reload the simulation, and I get basically it walks you through the entire process again. So since it is walking me through the process again, I'll now take the time to actually find out some mistakes. So the most basic mistakes you can make are, of course, doing things like, for example, time duration. Let's say I put -1, okay, and I try to save this. It tells you there are errors in the form. So this is, it gives you this, it actually screams at you, and it actually tells you where the error was. So it says the time limit must be greater than 0.0. That's what it says. You can't have a negative number. So let's go back to 0.5. Now, okay, to check whether it's okay, you just click. If it saves, it means it's okay. Alright, that's what it means. If you're able to save simulation parameters and get this page, it means what you have saved, the parameters are okay. Now let's go to the next step. The next step I said was there's the integration time step. The integration time step is the time step of the solver, that is the ODE solver, because we are solving differential equations and you need a time step for that. The time step is 1 microsecond. The time step for data storage has to be greater than or equal to the integration time step. Why? Because the integration time step is the time step at which you're solving the equation. You cannot generate data faster than that. It has to be slower than that, or it has to be at the same rate. So to check that, I'm now going to change this to 1 microsecond. So they're both equal. Let me save this, and it's okay, because that's perfectly legal. You can save it. I think you can save the data at exactly the same rate as you generated by the solver. That's okay. Now I'm going to try the other way. I'm going to try to make the data storage interval lower than the integration time step, which means I am now trying to save data faster than I am actually generating it. There should be an error, and I will show you. And you click on it, it says there are errors in the form. Says, see, this number must be greater than or equal to the integration time step, which is the previous value. So this, it actually tells you this integration time step has to be, this data storage time step has to be smaller than the integration time step. So we can get rid of this error by decreasing it back again, and it's okay. Now in terms of dat file, as such, I don't think there is anything. Let me change this to circuit output.txt, and it's okay. So as long as it's a text file, it is okay. Let me try XLS, or let's try JPG. And actually it does. Now this may sound strange, but whatever you use is going to be a text file. Okay, it's a text file that you can actually open and read in Notepad or gedit or WordPad or any of them. Okay, so there is no restriction on what it can be. So I'm going to go back to that anyway, because there's no point in doing this. So the last, now as for this, let's say for example, let's say I say I want to slice the output, and I leave it at number is equal to 1. I save it, and it says that error is in the form. Why? Because when you want to slice the output data file, it says the number of slices has to be at least 2, so that is 2 or more, because if there's only one slice, then there's no point in even slicing the file. What does it mean to slice the output file? What it means is this output data file will be broken up into chunks. So if you say you want two of them, there will be 2 such output data files, one is circuit output 1.dat and the other circuit output 2.dat, and these will be of equal size and they will be divided into equal time intervals. So circuit output 1.dat will be for 0.25 seconds and circuit output 2.dat will be for the next 0.25 seconds, and in this manner you can divide into as many you want. You can even have 200 if you want. The main advantage of this method is when you have a really large simulation, let's say you're simulating 10 inverters. In that case, if you're simulating 10 inverters, you might also want to generate data. You might want to plot data using other softwares, like you might want to plot it using GNU plot or any other plotting software. If you have a specialized plotting software, you can try that out. Now when the simulation is really large and you're simulating it for, let's say, 10 seconds, the data is so huge that actually just reading that amount of data and trying to generate a plot can actually cause a plotting software to crash. So the only way to not have that happen is that you actually break it up into smaller files and you plot only those intervals that you need. So you know which intervals are those, you plot those intervals that you need. This makes your data actually much more manageable. And of course, if you want the entire data, you can plot that as well, but you'll have to wait for it. There's nothing you can do, because the larger the amount of data you have, the more you have to wait. So I'll just go back to no, because I don't really need this. Let's go back and save, and there are no errors, so we are back to okay. Now this last one, this is extremely important. The reason, as I said before, is this is the directory with circuit files. There are 2 functions it provides. One, this is the directory in which it expects to find all the circuit files. Number 2, this is the directory in which it will save the output data file, and it will save the images that it generates when you generate a plot. Okay, when you click on the plot button at the end, it will generate a PNG image, and that PNG image is going to be saved in this directory. So this directory is extremely important. To know what it means, I'll just show you where I am. Let's say this is my folder browser and this is where I am. So this is the directory, and just to confirm, I'm going to go and click properties, and this is the path: home, shift-mar, virtual environment, diode rectifier. So let's go back and check here. That's exactly what it is: home, shift-mar, virtual environment, diode rectifier. Okay, let me do a little change. I'm going to delete one letter, so I'm going to make it diode rectify. That is, this is wrong spelling. Let me try to click, and you see, cannot write into this directory. All right, what does it do? And I'll show you what this means. In this, you will find a file called test file. This is not a file you created. This is a file that the simulator creates. This is an empty file. Okay, I'm going to open this file and you see it is empty. Let me click on properties. This is 0 bytes. It is an empty file. It is just a file that is created, and the reason why it's created, because the simulator needs to test whether the directory exists and whether the directory can be written into. That's very important. So I'm going to go back and click rectifier. Now, why did I say you must be able to write into? Now, at this point of time, I need to tell you something, and that is this circuit simulator should always be run as a user. Do not run the circuit simulator as an administrator. Alright. Number 2, do not run this, do not put this directory into a folder which is your root folder. Like for example, even if you are on Windows and you are running it as an administrator, do not put it in C program files or something like that, which is critical. Why? Because if something happens and this ends up deleting some important files, and I can't guarantee, because this is a software which is in development, and it deletes some important files, your system could be unusable. So never run this circuit simulator as a root user, and never run this simulator in a folder which is a root folder. So I'll give you an example of what this means. I'll go back a couple of steps and let me go into super user. I'm going to go into super user. So now I am the root. Okay, check it out. This means I am root. In the root, I'm going to create a folder. Let's call this diode test. Okay, because I just want to test it out. So this folder diode test now exists here. Now to tell you what this means, let's look at the folder. Diode rectifier was the folder I was using before. It was created by the user Shiv Kumar, which is me, and the user has all right properties. Now this new folder which I've created as root, and it is only the root that has all right properties. Okay, check it out. These are the properties the root has. These are the properties that the others have. So this is the property that now the user has. You see, there is a write property, there is execute property. There is no write property. There is a read property, there is execute property. I'm sorry, there is no write property. So what that means is, now let me try to put this one. I'm going to try to specify this new folder that I've created, diode test. And there were errors in the form. Now here I must say this folder exists. Let me go up here. You see the folder and you see there's a lock. What this means is you as the user can't do anything to it. And there is no test file. Because what actually happened was this simulator tried to write that test file in this directory and it couldn't. And the reason for that is simple. It does not have permission. And therefore it failed. So in order to have this, so this is very important. You must make sure the directory exists. You get the path right. And as I said before, the best way to get this path is just go to any folder. Like you click on a file, click on properties, and you can do this in Windows and in Linux. Just double click on the parent folder. You get the entire path. In Windows, this will probably be path. But either way, this is what you should copy and paste it. Alright. Also, make sure that this is writable. Do not create this folder with another user and try to use the simulator with another user. Like for example, you have a user X and then you try to use the simulator with another user Y. That probably won't work because user Y does not have write privileges into the folders created by user X. So with this, I'm going to save this, and I think now we are okay. So these are all most usually the errors which happen in this page. Alright. Time duration, pretty obvious. Here, this is a mistake many people make. You must make sure that the time step of data storage is greater than or equal to the integration time step. Don't make them, you can make them equal or make them greater, no problem. But the data storage time step cannot be smaller than the integration time step. If you want to slice the file, make sure the number of slices are 2 or more. Output data file, try to use dat or txt. You can use anything you want. It will still be a text file, but it may be confusing if you're using Windows or something else, because then it will use the extension to apply the file or apply the application which can open it. So you don't want to get into that mess. Don't try to be too experimental with this. Use dat or txt. And the most important, the directory with the circuit files. Get this absolutely right. And the way to get this right, go to your browser, or rather folder, click on a file, copy the path. Okay, now that we're done, let's continue. So now, in terms of circuit files, there was a few, like I said, source.csv and these things. Now let me show you some very simple mistakes that happen. So the first step is, let's say I am now trying to add, like I said, the working directory means the simulator expects everything to be in this directory. So I'm going to take one file and I'm going to move it out. Okay, I'm going to move it out of this working directory. So now let me see if I can add this file. Okay, so this is what it shows. Diode rectifier is the folder. So everything is in here. This is where all my files are. And now I'm going to try to open this file. Okay, so I'm opening a file that is not in the working directory. So let me save this, and you see, okay, now actually this is wrong. So basically it just took the same name. So I'm going to rename this file. Let's rename it and call this direct1.csv, just to make, because there are two types of errors, and I'll show you that again. Okay, so let's try to add direct1.csv. So let me save this, and you see the circuit spreadsheet could not be read. Make sure it is in the same directory as the working directory above. So it just says, you told me to add a file, but I can't find it in the circuit. I can't find it in this working directory. It's not there. So just make sure that it's in the working directory and it's readable. You don't want to create it as a root user. Again, do not create anything as with another permission that this user cannot read. So that's error number one. I can just get rid of this. So now the next part is, let's again go to this and I'll show you the other error. Let me open this file and let me save this as an Excel sheet. Like I said before, all circuit spreadsheets have to be saved as CSV files, because CSV files are text files. So now what happens if I save it as an Excel sheet? And I'm going to do that. So I'm going to say save as, and let me save this in this form: Microsoft Excel 2007 to 2013 x.xlsx. So I'm going to save this in this form in the same directory. Okay, now it also gives me this warning because in Linux, which is what I'm using, it uses the open document format. So it's still saying, are you sure? And I say yes, I am. It's not a problem. So you see, this file has been saved here, and now it has a different meaning. See, these were all text files. This is an Excel sheet. So now let's go and add this. Now there's a slight mistake. Again, I have to rename it, and I'll show you this error a little later. So I'm going to try to rename this. I'm going to try to add this. So I'm going to try to add this file direct1.xlsx. So I've added this, and let the schematic description be the same. And you see, it gives you an error. It says the circuit schematic must be a .csv file. It will not add anything else. It will not even add a .odf file. It has to be a CSV file, because a CSV file is a text file, and Python can read a text file without any problems. Alright, so that's number one. Now the next part is, and this is something which I've been saying, let's try to again add direct.csv. Now we've already added direct.csv. You see here, there are three files, and direct.csv is the second file. This is the diode bridge. This is the circuit of the diode bridge. So let me try to add this again. Okay, we already added this. Let me try to add it again. And you see, it says circuit schematic has already been added. So you cannot add circuit schematic again. Alright? For the first and foremost, there's one problem which is there, is when you have a really large circuit with a large number of circuits. Let's say such kind of sheets. Let's say you have 10 inverters, or you have an entire power system, and you have 30-40 sheets. It's quite easy for you to lose track and add a circuit which you already added before. Alright? And the reason why I did this is because there were times when I was actually simulating and I found I was making this mistake. That is, I was actually adding a circuit which is already being added before. And the problem when that happens is now the same circuit is being added and this circuit has exactly the same components, the same jump labels and everything else. The result is there are going to be errors. Why? Because you cannot have two components with the same name. You cannot have two resistors with the same name, let's say R1. That's a violation. But if you add the same file again, you will have that problem. Alright? So that's the main reason. So now, another thing is, okay, this is usually the common thing. Let me see. So now, one thing I need to tell you is, let's say for example, now this particular number 4. Now, we were working on number 4. We were thinking, or at least we were looking at ways in which we could add this fourth circuit. But, remember something, until you click on save circuit file, it won't save. For example, if I click on save circuit file, now I haven't chosen anything. So it says circuit spreadsheet could not be read because I haven't chosen anything. But until you save it and it appears here, it has not been added. Okay? So like for example, let me delete this and let me copy it and let me add it. So there's a direct copy.csv. So let me add that. Okay. Now, if I just leave it as it is, this file has not been added to this simulation. All right. In this current state, it has not been added. So if you just choose this file, click on it from this browser and leave it at this stage, it's not going to work. Okay. And it will work like, for example, let's say for example you've done this and you want to add the fifth file. I say okay, add circuit file. You know what? I get back number 4. That file which we chose never got added. Why? Because we didn't click on save circuit file. So if you want that file to show up, do not forget to click on save circuit file. Right? Now it appears because now it has been added. When you save it, it adds it. If I add circuit file here, you get a dialog box. But if let's say I change my mind, I don't want to add it, you don't have to think about it. Forget it. Don't worry about it. Alright? You don't have to think, oh, there is no delete button. What do I do with this number 5? Until you click on save and it appears, nothing has been added. Only these have been added. What appear in this form and what appear with this remove circuit button. So now this direct copy is a wrong file. I don't want it. So I'm going to remove it. And to remove this circuit, you click on this remove circuit button. Alright. So this is it. So now I'm going to process just to say whether everything is still okay, because last time we simulated and it was okay. So it says circuits do not have any detectable errors. So now that we've done this, I'll show you some other errors that happen in the circuit. Okay. So let's look at this. This is my circuit. Okay. Now, what is one possible case which can happen? First is there is a library of elements which are there. Okay. For example, resistor, inductor, voltage source, capacitor, diode, switch, control voltage source, and voltmeter, ammeter. There are a few. If you really need to know, I would suggest go to the website and look for a document which tells you all these elements. If not, I'll try to create one. Otherwise, the book has the entire details. I published a book and that book has everything. But let's say, for example, here, as I said before, the underscore is the delimiter. So everything before the underscore is the name of the element, or as the type of the element. Everything after the underscore is the name of the element. So this is a diode with name Direct1D1. So let me make a mistake here. Alright, let me delete this. So I'll call it DD. That's wrong. It's a mistake, spelling mistake. Okay, I'm going to save this file. It says it has been saved. Don't worry about it. It has been saved. Now, if you make any change to the circuit, like what I just did, all right, if you change a component, if you change a structure, if you, let's say, add another branch, if you add another element, if you touch this file in any way, you must go back and run process circuit schematics. All right. If you change the parameters, you don't have to worry. But if you change the circuit, if you touch it, if I put, let's say, another wire, or I delete a wire, or I put an ammeter, or I do any of that, you must come back and say process circuit schematics, because you must check whether the circuit is okay. Alright, so now that I made this mistake, let me click on it. Okay, this, am I clicking on the right file? Oh no, I'm sorry, that's the reason why, because I'm clicking on the wrong file. I clicked on the Excel sheet. So let me open this again, say OK, because the Excel sheet is not a part of the simulation, it is this file. So let me make this mistake again here, save it, and now let's come here, and now that this change has been made, let's click on it again, and you see now there is an error. It says there are errors in the circuit. Error, component at 4E in sheet direct.csv does not exist. So it tells you which sheet has the problem, number one. It tells you which cell has the problem. It's 4E. So let's go look at 4E in direct.csv, and this is 4E. Alright, this is exactly the mistake I made. So it is telling you this component does not exist, and it does not exist. There is no component called Diode. So let me go back to diode. Let me save it again. It's important to save it. Let me come back to this. Now here at this point it expects you can't do much because there isn't, the process is gone. Okay, so you, to make sure you get it back, all you have to do is just add the circuit. As I said, don't care about this. I'm not going to save it, so there's not going to be anything added. What's important is I have reset this process. So now I get back the process circuit schematics button. I click on it, and now we're back to OK. So that was the only error, and I changed it. So now let's go make another error. So now, as I said once before, two components of the same type cannot have the same name. So let's make that mistake. Let's call both of them diode D1. Okay, there were D1 and there was D2 because it's a leg. Alright, it's a diode leg. And let's come back here and let's click on it. And it says there are errors again. So these are errors. Duplicate labels found for components of type diode at 4E in sheet direct.c. So it tells you which sheet, and it tells you that these two components have the same label. So let's look at 4E and 16E. This is 4E and this is 16E, and it's saying these two have the same name, and yes they do, they have the same name. That's a violation. You can't have two elements of the same type having the same name. So let's go back and change that. So as before, we've lost this because there is an error. All you have to do, just click add circuit file and you get process circuit schematic again. Let's click on it and we are back to normal. Okay, let's make another mistake. Now, whenever you use a jump label, there has to be another jump label. See, for example, this is one jump label. And this is the second. So this is how, using jump labels, I'm connecting these two branches together. I'm connecting this load branch with the output of the diode rectifier. Alright. Now, when you use a jump label, there's one rule there are several rules you must follow. First is, the jump must always occur in pairs. So if I have one of these, there must be only one more somewhere else. Alright. You cannot have 3 jump labels of the same type. You cannot have 4 jump labels of the same type. And you cannot also have 1 jump label of that same label. So, supposing I delete this. And I come back here and I click on it. And it says, check jump label and at 1A in sheet load.csv. So it says, look at this jump label in load.csv. this jump does not have a corresponding jump label. What it means, it has to have a pair. There has to be another one of this jump label. Otherwise, this segment cannot be connected to anything else. Alright? So that's what it means. So let's go back here and add this. Let's come back as before. To reset this, let's click on process circuit schematics, and the error is gone. So always remember, when you have a jump label, make sure that the jump label occurs in pairs, never alone. Okay, and never even in multiple. So you can't have 4 jump labels. Now let's do one more thing. Let me bring this right next to the node. So this is the node. Okay, this is a node because it's connecting, and let me bring this right here. Now this may seem like a legitimate connection, but it's a mistake, and I'll show you why. So you see there are errors. Check jump 1j in sheet direct.csv. Jump label is adjacent to a node. Now let me come here and let me show you jump. It is 1j. So this is 1j. Now what is a jump label? A jump label connects 2 parts of a branch segment together. Alright? And this is very important. It connects 2 parts of a branch segment. Now, to call it a branch segment, this is not a branch segment because this is just next to the node. Alright? You cannot extend a node. You extend a branch. By putting the jump label next to the node, you are extending a node. This is an ambiguous connection. Alright? This is a clear connection. Here, this is a branch. This is a branch that is starting from this node, and you are connecting this branch segment to another part. That's okay. But if you put this jump label right here, the node, you are extending the node, and that is ambiguous and the circuit will not work. You cannot do this. You must have always at least one wire element or any other element next to a node. I would say when you have a node, always put a wire element next to it. Never put, like for example, do not put a resistor here. Let me just put that. Resistor trial. Let's call this resistor trial. Now, let me come back here. Did I type it right? Yeah, I typed it right. It's resistor trial. Let me come back here and let me reset this error. And let me process circuit schematics. It says no error, but I would say please don't do this. Alright? Do not put an element just right next to it, to a node. This is an ambiguous connection. A node, if it has wires on all sides, it is always clear that this is a node and it's extending and radiating in all directions. Alright? A jump is totally illegal. Alright, that's why the error, the circuit and the circumvention will throw an error. Even putting a resistor, I would say do not do that. It can produce unpredictable results, particularly as the circuit grows. Alright, particularly when you have lots of connections and things like that, it can produce unpredictable results. Next to a node, when you form a node, always put wires on all sides. Alright, like for example here, this is a node. Put wires on all sides. Okay, so now that this is done, one other thing, in this circuit simulator, every branch must be completed. So a branch is any segment between 2 nodes. So a node is a connection of more than 2 wires. So let's say, for example, let's say I take these 2 wires. This is a part of a branch. There are 2 wire elements next to each other. This diode and this wire. These are 2 elements next to each other. That's a part of a branch. But now let's look at this one. This has 3 elements on each side. It becomes a node. Alright. Similarly, you can have a node with 4 elements. That's also okay. That's what you call a cross. Right? So when you have between 2 nodes, there is a branch. When you must always complete every branch between 2 nodes. Never leave a node broken. For example, let's say I don't want to connect. Let's say, for example, let's go to the, okay, I've been fiddling around with this circuit a lot. Let's go to the node, load. Let's say, for example, now you change your mind and say, I don't want to load this diode rectifier. I want this diode rectifier to work at no load. So you say, okay, you know what, I'll break this branch. Okay, that's what I'm doing. I'm breaking the branch. So you see now the diode rectifier is open. The switch is open. This branch is open. So the diode rectifier is at no load. Now, this may seem like a legitimate operation, but it is not. I'll show you why. Now, when you process the circuit schematic, it will give you an error. So you see, there is an error. Check branch continuity at 2G in load.csv. Circuit error, branch is broken. Must close all branches. So you cannot have, so this is 2G. So this is 2G, this is 3G. So it's saying at 2G there is an element, next to it there is nothing. It can't continue. The circuit simulator just cannot continue and form the branch. It has to form every branch. If you want to open a branch, that is, you want to make a branch infinite resistance and make it draw low zero current, close the branch, put a resistor with a very large resistance. So supposing, for example, I was to run this diode rectifier at no load. This resistor load 1 can be made to be 10,000 ohms, 100,000 ohms, whatever you want. But you cannot break the branch. You must complete the branch. Alright? So now let's go back and reset that error. And let me process the circuit again. So that's it. It's done. So now that this is done, I think these are most of the common errors which are there. I don't think there's anything else. And in terms of edit circuit parameters, I'll just go through. There are a few which can happen. Some which are pretty obvious. Like for example, let's say I take the inductor and I give it a negative value. Okay. Give the negative value to it. I save it. And it says inductor has to be a positive number. This is pretty obvious. I don't think I have to actually do anything. I just a bit of idiot proofing in case you by mistake press the negative number. But this won't happen. Other than that, another thing, let's say for example, you have any element with a direction. Let's say for example, okay, let's take the voltage source. The voltage source has a direction. The voltage source, let me open this file. So now the voltage source has a direction. It is at point 1D and the positive polarity is towards 1E. So let's see what that means. The positive polarity is towards 1E. So that's what it says. Component position 1D, positive polarity 1E. Okay. Now, the important thing here is you must, this positive polarity, this direction, or rather the component direction, has to be somewhere on the branch. Okay. So let's say for example, let's go back here and let's choose something which is not on the branch. Let's say I choose it here. Okay. I make it 3J. So this is the branch. Okay. From here all the way here to here. This is the branch. Alright. This one 3J is another branch. This is the voltmeter branch. So let's just put it as 3J. And I'll show you why. Let's call this 3J. That means I am showing the direction is not on the branch, but is somewhere in that direction. So do not think the direction. So let me click on it. So it says polarity has to be an element on the same branch as voltage source. So when you choose the direction of a component, do not choose the direction as southwest, northeast. Do not think about it that way. It has to be an element on that branch. It has to be pointing towards that element, alright? But it has to be on the branch. Do not choose, like for example, here it actually seems like it's okay. I mean, I want this voltage source to point in the right, towards the right. The positive polarity is towards the right and 3J is the right, alright? You may think that's okay, but that's not okay. Why? Because it has to be somewhere in the branch. So it can be anywhere. It can be anywhere between 1I and 3E. So let's just make it 1I. Even 1I will work. So let's make it 1I. And it is okay. But it has to be on the same branch. Alright? That's something you must know. Do not put it somewhere in another branch. It will give an error. Do not put it in the same direction. You might think it's the same direction, but it's not. Besides this, there's not much. The others, if for some reason your circuit does not work or does not work as expected, usually go through these directions, particularly the direction of the voltage source, direction of the meters. Just make sure, like for example, quite often what happens, there's a component position, there's a positive direction. Quite often there is a possibility you might make the direction to be the other way around. So it's actually 5J, which means the voltmeter is measuring a voltage with the positive polarity towards the bottom. So let's say for example, this voltmeter, the positive polarity is towards the bottom. Circuit will work. It's just that the voltmeter will give a negative reading. That's not exactly right, but that may confuse you. If you see something like that, just check your parameters. That's it. Other than that, not much. There's one thing which I should talk about, and that is in the previous circuit we found there was a certain mistake. Now I'll just go back. I don't want to run the circuit again for that meter. This was the output. Alright, this is the output of the current. Blue, that is the green, is the current, that is a spiky current, which is right. Blue is the voltage, that is the source voltage measured by the voltmeter, and the orange line is the output voltage of the diode rectifier. Now you see there are a couple of problems. One, there is a huge ripple in the diode rectifier output, and when this diode conducts, alright, when this conducts and the current is a peak, you see the voltage drops drastically, and the reason for that is because the inductor is very large. So let me now in this case change this. Let me change this. So let me change this and make it, let's say, 100 micro. So now it was 1 millihenry, I'm making it 100 microhenry. Okay, this is 10 times lesser. Nothing wrong with that, you can change it. Matter of fact, you can change it to whatever you want. I would recommend you should, because that's what a simulation is for. You can actually try things out without blowing it up. And now here I won't talk about control. When you talk about control, a lot of very different kind of errors will come, and I'm going to talk about that in the control lecture. So let me just view the output. Here as before. Now in this case there's not much can happen. The only other thing I should do is when you click on run, okay, I'm going to run the simulation now. Let me just, there's one thing. Sometimes it's a good idea to copy this, because what happens is, if you want to preserve this output data file, okay, when you run the simulation again, it will create a new, it will delete the old output.dat file, this circuit output.dat file, and create a new file. So if you wanted this old file for some reason, you've lost your data. Alright, that's a problem in case sometimes, because it's lost work. So unless you're sure that the simulation is junk, I would suggest copy it and save it. Like in this case, I just want to save it. I don't really need it, but I'll save it just in case. So I'm going to run the simulation, and here you will get this output simulation is running. But sometimes, and this will be a problem particularly in the when you have control functions, the error appears in the command line. Okay, I still have to work on it, and because the reason is, if there is a syntax error in your control function, that will not appear in the web browser. That will actually appear in the control, that will in the command line. Now I need to work on this and try to figure out if, and try to transfer this output from the command line to this, what do you call it, to the web browser. Let me see how I can do that. But for now, whenever you click on the run button, even if you don't see an error, if you see an error, wonderful, but if you don't see an error, go back here to the command line and just check once if everything is okay. Okay, so in this case everything is okay, so there is no error, the circuit is running. So as before, let's plot these values. So let's plot this one. This is the plot we were actually worried about. So let's plot it. So this revolving button means it's working. So it's taking some time, and I'm surprised it's taking time. Usually it doesn't. We have caught some kind of a bug. If that is the case, all we have to do, run the simulation again. I'm not sure what happened. A whole host of things could have happened. This could have actually been something with the Python compiler. It could have been with Django server. It could have been n number of things. Usually it does not happen because we didn't see an error output. Yeah, okay, so you see there's an error output. So this what it means, it's saying broken pipe. Now, a broken pipe is a problem which is slightly more complex. I can't talk about it now. I'm not sure if this will also work. Let me see. Okay, it has worked. So a broken pipe, what it actually means is this is the way the Python interpreter works. So the Python works on what is called as a global interpreter lock. I won't go into the details, but that is like a thread. When a Python process runs, it runs on a thread, and sometimes this thread breaks for unknown reasons. It could be operating system, could be anything. But so I'll look at it, and you see now it's totally different. Let this program run a little. But you see now it has been replaced by these two. Instead of one large peak, it has been replaced by two peaks. Let me come back here and plot it again. And let me see. Yeah, so you see here it is very different. There is still a huge dip, but you see now, you see the blue line. Okay, let me just zoom in. 0.06 to 0.08. That's a valid range. Let me zoom in that range. And this is how, this is how you debug any circuit. You just you click on the entire thing, look at any interval that interests you. Maybe there's a bug, maybe there's something that you need to fix. In this case, we are wondering what happened. We just want to see how the plots look like. So I have zoomed in to that 0.06 to 0.08 range, and you see this is it. So 0.06 to 0.08, and you see it's totally different. Alright, it is very different. Now the reason why you see here, the reason why it's different now is there isn't such a huge glitch. The glitch is mainly when at this point, you see, this is when the diode rectifier starts drawing a current. And it starts drawing a current for the simple reason that the output voltage is lesser than the blue line. Now look at after that what happens when this stops conducting. That's when the output voltage drops. And the reason why it drops is because we have a large resistance at its output. This large resistance at its output is discharging the output capacitor. And when the diode starts working, when the diode rectifier starts conducting, it starts drawing a current. But you see here, now here these two are kind of superimposed, but you see here this point, you see this is the negative term. There is a dip. There is a dip in the output. Alright, because this dip means when the diode rectifier draws a current, that drop across the inductor and the resistor is causing the voltage appearing at the input of the diode rectifier to drop. Alright, this is just Kirchhoff's voltage law. This is just drop across the inductor and the resistor, mainly the inductor, not even the resistor. The resistor is like 10 milliohm. So what this means is, this tells you how the loading of the diode rectifier will impact the working of the rectifier. The more you load a diode rectifier, the more the input of the diode rectifier, the input voltage of the diode rectifier will drop when the diode rectifier works. So this gives you an example. So what does it show you? When you are designing your diode rectifier, typically this inductor, and I'll just go back, this inductor in reality is the leakage reactance of a transformer. Alright, is the leakage reactance. Nobody actually connects an inductor. Very few people actually go and connect a large inductor in the input of a diode rectifier. Why would you want to spend all that money there? The reason is, when you are connecting a diode rectifier at the secondary or at the secondary of a transformer, this could be a step up or step down transformer, the inductance, the leakage reactance of the transformer comes in series. the more the leakage reactance, the more will be the drop across this leakage reactance, and the less will be the voltage that is fed to the diode rectifier, because this is the voltage fed to the diode rectifier. This is the voltage measured by the voltmeter fed to the diode rectifier. So the lower you are able to make this leakage inductance, the more voltage that you get at the output. That's what it shows. That's what the simulation shows. So now it's not possible for me to go into a lot of other details. At this point, I'll have to stop this lecture. But these are the usual errors that you will find at the basic level. A lot more complex errors will come once we start control, and that will be the next lecture. Because what I'm going to do, I'm going to stop. Okay, let me just stop the simulation. I'm going to stop the simulation. I'm going to stop this lecture, and the next lecture, I'm going to go to this last stage. And as I said before, this switch, this resistor, there is one resistor connected constantly between at the output of the diode rectifier. Another resistor is connected through a switch. All right. So this switch is always open. So the resistor is never connected. But now what we're going to do, we're going to switch this resistor. We're going to turn it on, turn it off, turn it on, we give it a duty cycle. And I'll show you how we can actually control this switch to run at such a duty cycle and what we can do. That will be the next lecture. But when control comes in, some fairly peculiar errors can come in, and I'll show you in detail, maybe in that lecture or maybe even in a part 4, what are those errors and how do we counter them. So for now, this is it. Shown you everything. This is the last. I'll just show you with these last results. The plots are fairly good. As I said, the end is always look into this directory. The directory contains everything, and you will find the same you'll find the plot file with the same name as the plot, except the spaces have been removed. So open it with anything you want, and the best part is in this plot there are scales, there are axes, and there is also a legend. So if you're looking for a quick report to make, this is something which is pretty easy. If you want to make a detailed report and format these, you will have to work a little more. Maybe you'll have to even generate your own plots. At present, this is all we can do. I will try to build in some more facilities at a later stage. So for now, I'll stop this lecture, and thank you so much. And as before, if you have any doubts, please do email me or contact me by any form you want. I will release the next lecture maybe next week or maybe soon. Thank you so much, and see you soon. Goodbye for now.